Good evening to all of you all. In this video, we wish to study rolling on an inclined surface. In a previous video, we studied rolling on an horizontal surface. We had an horizontal surface at rest and there was a body rolling. It had an angular velocity omega. It had the center of mass had a linear velocity v. Omega was with respect to the center of mass. It was omega, the angular velocity with respect to an axis passing through the center of mass, and v was the velocity of the center of mass. Rolling, we saw, is a combination of pure translation and pure rotation. Pure translation and this is pure rotation. Combine both and you have rolling. Now, the point of contact was of importance to us. That is because at the point of contact, frictional force was acting. Frictional force acts. The role of friction is to induce or achieve pure rolling. Why do we say this? The nature of friction is to prevent slipping, and when there is pure rolling, there is no slipping. So therefore, the role of friction is to achieve pure rolling if it is not there. So if you have a body like this, a round object like this, the tangential velocity at the point of contact is omega r, because the angular velocity is omega. So tangential velocity omega r with respect to the center of mass. The velocity of the center of mass is v. So superimpose that on the tangential velocity to get the absolute velocity. So the absolute velocity was omega r plus v vectorially. Now when there is pure rolling, this v and omega r will be equal, so that the point of contact is at rest. The horizontal surface also, we are assuming it to be at rest. So when both are at rest, we would say that this round object is pure rolling. If you differentiated this, derivative of the velocity of the center of mass will give the acceleration of the center of mass, and the derivative of the angular velocity with respect to the center of mass will give the angular acceleration alpha with respect to an axis through the center of mass. So v equals to omega r gives us a equals alpha r. Now let us consider rolling on an inclined surface. Supposing we had an inclined surface and this angle is theta, what we are going to do is we are going to have a disc. The disc, we are going to spin it and leave it on the inclined plane. So the disc, we shall spin it at omega naught. The disc has got a mass m. The disc has a mass m and a radius r. Mass m and radius r. You are going to spin it and leave it that way. So what are the forces? If we draw the free body diagram, mg can be resolved as mg sine theta acting at the center of mass. Mg cos theta would be like that. There would be a normal force n like that. N would be equal to mg cos theta. Now if you saw the point of contact, the point of contact has a tangential velocity omega naught r to the downward, in the downward direction. So there is a slip in the downward direction. Therefore friction would act in the upward direction to prevent the slip. Now because there is slipping, we can say friction would have reached, or friction attains its maximum possible value. So F will be equal to F limiting. F limiting is mu n, that is mu mg cos theta, because n is mg cos theta. Now let us see what happens. Now three cases really arise. We'll study each case. The first case is where this frictional force is greater than mg sine theta. The second case we would like to take is mg sine theta is greater than uh, the frictional force, and third case is where both these are equal. So let us study each of these cases. So first, to study translation, we treat the entire body to be concentrated at the center of mass, put all the forces at the center of mass. So now what we are going to find here is that if you put these two forces, frictional force and mg sine theta, on the center of mass, the acceleration of center of mass will be upward because we are assuming frictional force is greater than mg sine theta. So acceleration would be net force F net divided by the mass. F net would be mu mg cos theta minus mg sine theta by m. So your acceleration is going to be mu g cos theta minus g sine theta. So the linear velocity, initial linear velocity of the center of mass is 0. So we can say v, the instantaneous velocity would be v, if you use v equals u plus at, v u 0, a is given by this expression, you will have v is equals at. You can put the value of a from this and get the instantaneous velocity v. Now this frictional force will cause a torque. This frictional force is going to cause a torque about the center of mass. That torque is in the anti-clockwise direction. The angular velocity is in the clockwise direction. So it is a decelerating torque. So let us see how much is that torque. The torque will be F into R, which is equal to the moment of inertia of the disk into alpha. F is mu mg cos theta into R, that is equal to I is mr squared by 2 into alpha. So R would cancel, m would cancel, you will get 2 mu g cos theta by R as alpha. So you can actually get what is the instantaneous omega. Instantaneous omega will be omega naught minus alpha t. Why minus? Because it is a decelerating torque. So it's an angular deceleration. So you can put omega is equal to omega naught minus alpha is 2 mu g cos theta by r into t. So you will have omega r is equal to omega naught r minus 2 mu g cos theta into t. 2 mu g cos theta into t. Here we have v is equal to 0 plus a is mu g cos theta minus g sine theta into t. And when a pure rolling occurs, v will be equal to omega r. V will be equal to omega r. So if you equate the two, you can get the time at which pure rolling will start. So you have mu g cos theta minus g sine theta into t is equal to omega naught r minus 2 mu g cos theta into t. So if you got that here, you would have 3 mu g cos theta minus g sine theta into t is equal to omega naught r, or t is omega naught r divided by 3 mu g cos theta minus g sine theta. That is the time at which pure rolling occurs. Now the moment there is pure rolling, friction for an instant at least should disappear because it has achieved what it wants. But If friction disappears for a while, see what happens. Will the pure rolling be sustained? Will the pure rolling continue? Let us see. Since friction has disappeared, there will be no torque about the center of mass. If there is no torque about the center of mass, this omega, which we saw during pure rolling, that omega will not change. But there is mg sine theta acting downwards. So V will decrease. So there is no torque and there is a force. There is a retarding force. So V will decrease and omega will remain the same. So V equal to omega R equilibrium, the equation will be upset. So therefore friction, even if it disappears for a while, will appear again, and it must appear in the upward direction only, because V has a tendency to decrease because of mg sin theta. Omega should also decrease. So if omega should decrease, it should be a decelerating torque. So F will act in the upward direction. Another point is that this F will now not be equal to the limiting value of mu mg cos theta. In fact, this F, if it is mu mg cos theta, and we had said mu mg cos theta is greater than mg sin theta, V will increase and omega will decrease. So that is not sustainable pure rolling. So therefore, the frictional force F, even if it acts upwards, must be less than mg sin theta. So what will happen is the magnitude of V will decrease because mg sin theta is overpowering the frictional force, and the torque of F will also reduce omega. So this way the pure rolling can be sustained. So now let us see how much will be this frictional force. We wish to calculate how much is the frictional force. We will once again write the acceleration. The acceleration now will be mg sin theta minus F. This F we said is not mu mg cos theta. In fact, it must turn out to be less than mg sin theta by m. This is the acceleration. What about the alpha? Alpha is going to be F into R, the torque, what we said there, and is going to be mr squared by 2 into alpha. Yes, mr squared by 2 into alpha. So 1 R cancels, and you have F is equal to m alpha R by 2. M alpha R by 2. Now since there is pure rolling, we said V is equal to omega R. If you differentiate this, you get A is equal to alpha R. So therefore, what we can do is, we can put alpha R as A. We can put alpha R as A. So therefore, you get A as 2F by M. So A would now be equal to 2F by M. This 2F by M, if you substitute here in this equation, you will get 2F by M equals mg sin theta minus F by M. M cancels and you will get F is equal to 3F. 3F is equal to mg sin theta. So you add alpha R, by 2, 2F by M. 2F by M is mg sin theta minus F by M, M cancels. So F would be mg sin theta by 3. So as expected, the frictional force is less than mg sine theta. Yes. So yes. Okay. Now let us see what happens as this moves up now. This V is going to decrease. Omega will also decrease. And there will come a time when it will come to rest. It comes to rest. And omega also becomes 0. Then the body starts its downward journey. The body will start its downward journey. When it starts its downward journey, omega is 0. There is an mg sine theta which is acting downward. There is no omega, there is no v. Both have reduced to 0. Now the v is going to start increasing in the downward direction. So this point of contact has a velocity v like this. Now there must be an omega r for pure rolling in this direction. So omega must be in this direction. So friction must act in the upward direction. So friction will continue to act in the upward direction and omega will keep on increasing, v will also keep on increasing and the body will roll down. Now let us take a case where the second case where mg sine theta was greater than mu mg cos theta. Let us take that case. This is the body here. You have mg sine theta. You have rotated this by omega naught and left it on the incline. Now we are saying mu mg cos theta is acting this way and we are now saying mg sine theta is greater than mu mg cos theta. If mg sine theta is greater than mu mg cos theta, the body will now gain a downward velocity. But if you see the situation, you have v downward, so at the point of contact v is downward, yes, and mu mg cos theta is causing anti-clockwise torque, so omega is decreasing and omega r is also this way in the same direction as v. So this is how the situation is. Omega naught r or omega r is this way. So there cannot be pure rolling in this condition unless the body starts rotating in the anti-clockwise sense. So this torque of mu mg cos theta will now reduce omega naught to 0 and make it rotate in the anti-clockwise sense, so that omega r acts in this direction. And when that happens, yes, there will come a time when, now when that happens, frictional force is upwards, and it is causing an accelerating torque. So omega r will increase, v will also increase because mg sine theta is greater than mu mg is greater than the frictional force, so it will increase. So v equal to omega r will be maintained at all times and the body will continue pure rolling. Again here, F will not be equal to mu mg cos theta, but it will be equal to this value. Yes. Then the third case was the case where mg sin theta was equal to mu mg cos theta, and we had left the body with an angular velocity omega naught. Now in this situation, the body will neither go up nor come down, and it will rotate in the same place, and because there is clipping, there will be heat generated. All the kinetic energy, rotational kinetic energy, will be dissipated as heat, and the body will come to an instant rest. Now, this mg sin theta, when it comes to instant rest, there would be no friction because the point of contact is at rest. Now, there will be a velocity generated in the downward direction. So, the point of contact will have a velocity in the downward direction. So, that is a slip in the downward direction. Friction will again act in the upward direction. There will be a torque, and there will be an omega generated like that, and omega r will be like that. V will be equal to omega r, and F will not be mu mg sin theta, but it will be mg sin theta by 3. Thank you.